Hey, welcome back. In this video, we're going to introduce Valgrind. This is going to be a standalone application that is going to be different from our compiler. We will have to add an additional flag. Well, the flag's been included throughout the majority of the semester for use since it's used by LLDB and GDB during debugging, but it's also helpful to Valgrind. So let's go ahead and take a look here. What is Valgrind? Well, Valgrind is going to be a tool that's going to provide a number of debugging and profiling tools which help you make your program faster and more correct. Again, we're not necessarily worried about performance in this course. We are worried about correctness though. So memcheck is going to be the most popular tool among the suite of tools afforded to you by Valgrind. It's going to detect many memory related errors that can lead to crashes and unpredictable behaviors. You can find memory leaks, invalid pointer use, and uninitialized variables amongst some of the different things afforded to you by this application. It will, I guess, save you hours of debugging. I certainly agree with that statement if you are using it correctly, though it will slow down the execution of your program some, again, because there's going to be a number of different things happening behind the scenes as it's being executed. So the compilation command for this will look at just like pretty much the compilation commands that we've been using throughout the semester, but what's important is that you do include this flag-G so that the debugging symbols are inserted into your application because it will allow Valgrind access to some additional information to provide better diagnostics. So if you want a list of tools, you can simply run Valgrind. So we've installed Valgrind within your CS128 environment. To invoke it, again, it's just writing the name of the application name, Valgrind, and it will provide some output to you, including a list of the tools that you're able to run. When you run your code, so we're going to compile it down to an executable, and then if we'd like to run our executable through Valgrind, we're going to, instead of writing ./a.out, we'd go ahead, or the name of the executable, so ./bin exec, whatever the name of that executable is that was generated during compilation, we'll go ahead and instead say Valgrind --tool equals memcheck, and then we'll go ahead and provide the path to the executable. So ./bin /exec ./bin, whatever you compile down to. If you have a memory leak, then the number of allocations and the number of frees will differ within your program. So if we go ahead and look, this is some of the output, and I'll go ahead and through an example show you kind of the output in its entirety of what Valgrind is telling you about your program. So here we have a summary of the free store. It says in use at exit, 40 bytes in one block. Total heap usage, 2 allocations and 1 free. So you can think about this in terms of the context of this class: 2 calls to new, 1 call to delete. And obviously this is communicating that a memory leak is presenting within our program because we have an uneven number of allocations to invocations of delete. So if we look at the summary, we can see that this is indeed communicated. We definitely lost 40 bytes in one block. Kind of what the number is perhaps, I mean, it's important, but for the context of this class, what's more important is realizing is, yeah, we definitely lost some data. So we definitely have a memory leak, and that's, reinforced by the information afforded to you up here. Okay, let's say the number of allocations differs from the number of frees. Well, you'll want to go ahead and rerun the program with the leak check option to give you more details about where potentially those leaks are presenting. So again, you could go ahead and actually just run it the first time with the memcheck tool enabled. I mean, that will be some additional processing behind the scenes, but that's fine. And you're going to go ahead and specify that, hey, what we want to occur here is going to be the leak check. So we'll go ahead and specify that as a flag to the Valgrind application. And then we'll go ahead and finish that up with the name of the program that we'd like to run. So let's go ahead and look here. We have a simple program. We're allocating an integer array on the free store. It's of size 10 and ends 4, so 40 bytes. And notice here, before we run off the end of main, we do not deallocate that memory. We can see here that Valgrind would communicate to us, saying that 4 bytes in one block are definitely lost in the record when we're using the leak check. And we can see here that there was a call to new in main, and there was nowhere else was there a deallocation of that memory. So that's pretty cool. That's pretty helpful. Let's go ahead and jump over to VS Studio Code and take a look at an example of this. So find my new share. We will go to VS Studio Code, and I have one memory leak example for you. So I'm going to go ahead and set this up, just compiling through and then going ahead and actually running Valgrind with the leak check enabled. We can see here we have an array on the free store of size 10. Its address is being stored in this pointer on the stack array. We can see here that, okay, there's, I don't know, we're storing the updated array size in this constant, and then we're simply allocating we're creating a new free store array of that specified size, and we're storing that address in array. And the reason why this is a memory leak is our only reference to this array was overwritten on this assignment, and we never deleted or deallocated the memory associated with this array before we made that assignment. So our kind of reference to this dynamically allocated array is lost. We're leaking memory because there's no way for us to go ahead and go back and perform that deallocation. So I'm going to go ahead and compile this down. I can go ahead and run this just without running it through Valgrind, and we can see here it's very unclear that a memory leak is presenting within our applications. And actually kind of in this simple example, we didn't experience any of the profound implications of a memory leak. But it would be nice to know if one existed, and if there is one, presenting within our application, where it is that we can address that. We do run Valgrind on your machine problems, particularly on the MPs where dynamic memory is involved, and we do expect you to pair nicely that number of every call to new with a call to delete, so that no memory leaks are presenting within your application. So I'm going to go ahead and run this through, and we can begin decomposing, the output of Valgrind within our CS128 environment. We can see here the free store summary. There were some bytes in use at exit, and we can see here that there were 3 allocations and only 1 free here. So in this case, what we are seeing is 1, 2. Not sure where that third one is coming from, but it was paired with a call to delete wherever it was. Obviously not in this. I'm guessing it would be an IO stream perhaps. But anyhow, if we go ahead and look at this, we can see that there are definitely, 2 unpaired, and it's going to be these 2, which never had memory deallocated for them as we fall off the end. So going ahead and looking at this, we can say 40 bytes in one block are definitely lost in record 1 of 2. It's that call to new in main at line 10. Oh, so this object never had its memory deallocated for it. So that might be some helpful diagnostic information, and tracking down the object whose memory wasn't deleted. And as we're going through here, you can see, okay, 80 bytes, 20 times 10, or 20 times 4, the size of an integer in this environment. We can see that, okay, there was some space allocated for that record. It occurred on line 13. So that free store object's also being, problematic. The one that was allocated with respect to this call to the new operator. So looking through this leak summary, we definitely lost the memory associated with these 2 invocations to new. So what we have to do is go back and figure out, how to clean them up. So with that in mind, we can see here that, running this tool with leak check, not only do we have kind of this summary in terms of, okay, well, yeah, we have this uneven invocation or uneven calls to the new, paired with calls to delete. And then what we can also see here in the leak summary is, okay, definitely, we definitely lost, the memory was definitely leaked. And then with the leak check, we can see exactly which objects were leaked. And this is going to be super helpful as we move forward in this semester. So that's Valgrind. That's, how to use it. We can see here the error summary. There were 2 errors from 2 contexts. And again, it really helped us figure out where those memory leaks were presenting, and we could, go ahead and figure out how to actually go through and debug those errors and where the proper place to deallocate the memory associated with those invocations of the new operator would be. So with that, we'll go ahead and close out today's lesson with a brief discussion on some of the other tools provided to us by the Clang compiler. But anyhow, that's Valgrind. I hope it seems pretty intuitive in the sense that memory was either definitely leaked or not, and kind of the number of calls to new were either paired or not paired with a equal number of calls to delete. And again, we need every call to new to be paired with the call to delete to ensure that memory is not leaked from our program. So with that, I'll see you in the next video.